Good morning. The future of catalysis as applied to the production of chemicals seems to be somewhat confusing, to say the least. In June of 1986, Chemical Week published a very extensive report on the current state of catalysis. And in this particular report, it was pointed out that industrial research in catalysis in the chemical industry was being dismantled, phased down, and dramatically curtailed. Now, at the very same time, we have the Incremental report, which identifies catalysis as one of the key intellectual frontiers in chemistry, and which recommends it as one of the top 5 areas for priority funding. Thus, we have a very wide discrepancy between the analysis and conclusions of the Incremental report and the perspectives and actions of the chemical industry. Now, it's important that we attempt to understand this discrepancy, particularly when we bring into focus the size and importance of catalytic technology. Now, the total worldwide, and this is different from the U.S. data given by some of the previous speakers, the total worldwide annual market for catalysts for petroleum, petrochemical, and chemical applications was estimated at $2.2 billion in a study conducted a few years ago by Chemical High-Tech of Switzerland. The average value of catalyst as a percentage of a product produced therefrom is conservatively estimated as 0.2%, and from these two numbers, one readily concludes that the worldwide value of products made via catalytic technology is in excess of $1 trillion per year. Now, this is greater than the gross GNP of all but a few nations in the world. Clearly, catalysis is a technology of major financial importance. There's every reason to believe that the societal needs that are served by the molecules and materials currently made by catalytic technology will continue. These needs will be served either by the existing materials or replacement materials made in either case, very likely by catalytic technology. What then is our situation? The abandonment of industrial catalysis research could perhaps be rationalized by assuming that the current slate of products of catalysis is surely of large volume, but rather low growth and apparent technology maturity. In short, it's unlikely that new advances will be made that would justify the replacement of the vast current existing technology and associated manufacturing infrastructure. Now, do we have here the same kind of neglect which has contributed to the decline in technology competitiveness that has afflicted our steel and other mature, low-growth industries? I believe the answer may well be yes, and that many current technologies are in fact rather vulnerable to displacement by radically new approaches or concepts. I will try to describe a few specific examples of possible opportunities for replacement of existing, relatively mature catalytic technology. Now, notwithstanding its current state of disfavor overall in the chemical industry, I believe that catalysis still has a bright future and an important role to play, but that its thrust will be quite different. In the recent past, when growth rates were high, or at least respectable, it was possible to justify a good deal of catalytic research on the basis of incremental improvements and incremental benefits. For example, for a world-scale plant of £1 billion per year, a reduction in manufacturing cost of 1 cent per pound provides an annual payoff on the order of $10 million. This is enough to pacify or perhaps at least tranquilize the corporate financial wolves. With low growth rates and general continuing overcapacity, however, the situation differs. Incremental advances are no longer acceptable. Major changes are needed. Discontinuities in existing technology are required. This is a very different ballgame for everyone. For management, it requires a much higher level of risk and patience than most managements are prepared to accept or are comfortable with. the scientists, it requires a much higher level of creativity, originality, and challenge. Now, in trying to address a specific need or opportunity for radically new catalytic chemistry, how does one proceed? I believe that there are a couple of myths around. One of these is that it is now possible to scientifically design new catalysts as a result of the great insights being provided by advanced instrumental techniques in surface science or in computer science. This is simply not true. These surface and computer science techniques have very much, greatly increased our ability to characterize catalytic materials and processes, but we are still very far away from being able to a priori design the catalyst, that is, to prescribe its chemical composition in order to catalyze a reaction in some significantly new way. Now, the most progress that I'm aware of in a priori design is in the area of homogeneous catalysis, and that is the area that I think most likely will enjoy the greatest further progress, at least in the near term. Now, in the remainder of my talk here, I'd like to consider the future of catalysis in terms of what new industrial developments can we expect in the future. These will be the result of either being able to do something not now practiced commercially, or being able to significantly improve some existing process. Stated another way, I'll try to identify some of the unsolved problems or limitations of current industrial catalysis, and in a few cases to suggest directionally what new approaches might be worth considering. Now, we see here the three key elements of any catalytic process, namely the raw materials of feedstocks, the catalyst, and the products. And in attempting to think about future developments in chemical catalysis, one convenient way is to consider these three basic elements and to project possible new developments that can be stimulated or driven by each of them. And today, in my talk, I'll just deal with the first two. First, let's consider the area of feedstocks. Methane has always been an attractive low-cost feedstock in those areas of the world where it's abundant and accessible. It's used to produce methanol, ammonia, hydrogen, and synthesis gas. Now, very obviously, one of the major unsolved challenges for catalysis would certainly be a catalyst that promotes the one-step direct oxidation of ethane to methanol. If such a catalyst were developed, it could have far-reaching implications. It might lead to the production of synthesis gas via methanol dissociation rather than the reverse process which we practice today, namely the formation of methanol from synthesis gas in a thermodynamically limited low conversion process which employs a large amount of recycling, both energy and capital intensive. The synthesis gas, in turn, is made via endothermic steam reforming of methane in many cases. Other uses can be seen for methanol produced via direct methane oxidation and synthesis gas derived from same. For example, synthesis gas could be shifted in the usual way to produce large quantities of lower-cost hydrogen. Recently, we've seen some new results in the literature that signal both increased activity and progress in selective methane oxidation, and some of that is being reported at this symposium, while at this conference here. While they're a long way from practicality over previous results, we should take heart in the knowledge that there are enzymes which can oxidize methane to methanol with very high selectivity. Personally, I believe that when practical systems are developed for the selective oxidation of methane to methanol, they will employ organometallic complexes at relatively mild reaction conditions rather than metal oxides at high temperature. Recently, we are also seeing new research results in which the products of direct methane oxidation are not methanol, but hydrocarbons coupled products such as ethane and ethylene. These results are also somewhat removed from current practicality, but great progress is being made, and these may be harbingers of important future developments. Methanol itself is an attractive feedstock even when produced by existing technology from synthesis gas. One particularly valuable new use for methanol would be its oxidative coupling to produce ethylene glycol, if this reaction could be controlled to proceed with high selectivity. Perhaps leads to such a coupling reaction may emanate from the exploratory research now underway in various laboratories on direct alkane activation, or from the increasing number of laboratories throughout the world that are taking a new look at hydrocarbon oxidation catalysis. Certainly one of the major advances in catalysis of the past decade has been the discovery by Mobil of the ZSM5 and related zeolites and their application to such reactions as methanol converts to gasoline or ethylene. Now, at the same time, and for the foreseeable future, these technologies do not appear to be competitive in most parts of the world with existing technology based on current hydrocarbon feedstocks. If, however, vast new sources of methane were discovered with an accompanying reduction in methane price, and there are a few profits, you can see this coming, and this was coupled with the development of new low-cost technology for direct oxidation of methane and methanol, the situation might change in a dramatic and revolutionary way. And in this scenario, of course, the dominant fossil fuel feedstock for methanol is methane and not coal as the alternate to crude oil. Also, of course, the production of gasoline from methanol, which is now practiced commercially in New Zealand, as illustrated in the photograph shown by Keith, could become more generally competitive. Normal butane is a feedstock that's both abundant and low in relative cost as a source of carbon for producing organic molecules. This low cost, combined with new catalytic technology, has led to normal butane replacing benzene as the feedstock of choice for oxidation to produce maleic anhydride. While butane is clearly emerging as a preferred feedstock, it's interesting to note that the present best catalysts used commercially for butane oxidation function at high temperatures and only afford about 50 to 55% molar selectivity. This obviously leaves considerable opportunity for improvement. Now, besides its existing uses, maleic anhydride itself is a potential feedstock for a number of reduction products, such as gamma-butyrolactone, tetrahydrofuran, and 1,4-butanediol. Butanediol is now a large volume intermediate for the engineering thermoplastic, PBT, and for other specialty polymers. The traditional route to 1,4-butanediol has been via Rebbe chemistry from acetylene and formaldehyde. Rather recently, several companies have announced their intention to produce maleic anhydride or to pursue its reduction to produce 1,4-butanediol. Lower cost maleic anhydride would decidedly solidify its attractiveness as a feedstock for making these several C4 oxygenates, and improved butane oxidation catalysis could provide the key to such lower cost. Also, very recently, Monsanto and DuPont have formed a partnership to develop a higher selectivity moving bed butane oxidation process. Finally, the feedstock we've been hearing about so much since the oil embargo of '73 is synthesis gas, carbon monoxide plus hydrogen. This is the feedstock that's potentially derivable from coal. While at first there was almost a stampede to learn how to make anything and everything from synthesis gas, there has later emerged some rationalization for chemicals, for chemical production in terms of the related economics. It's now rather widely recognized and agreed upon that for the foreseeable future, the only organic molecules that can be made from synthesis gas at competitive economics are small molecules with a relatively high oxygen to carbon ratio. In general, it appears to be uneconomical to synthesize a methylene group from synthesis gas. In essence, it's an inefficient and costly process because it involves taking a hydrogen-rich molecule like methane, converting it into a hydrogen efficient one, namely carbon monoxide, and then reducing it back to the hydrogen-rich moiety, namely the methylene group. With these economic facts of life at hand, there are very few new syntheses based for chemicals based on synthesis gas that offer much potential. Now, for almost a decade, it appears as though one major driving force in industrial catalytic research in the chemical industry was the effort to make chemicals from synthesis gas. The disappearance of that thrust has left a vacuum. Now let's move away from feedstocks and look at the catalyst per se as a driving force for the emergence of new catalytic technologies. There are three types of catalysts that I believe have very high potential, a major impact in new catalytic technology in the future. Namely, homogeneous catalysts, molecular sieves, and membrane reactor catalysts. In recent years, however, it's become clear that many of the so-called homogeneous catalysts can in fact be prepared and used in a variety of solid-state forms that have basic catalyst properties, activity and selectivity almost identical to their soluble liquid-phase counterparts. What we have called homogeneous catalysts for so many years should in fact be called metal complex catalysts. Our second group of major impact catalysts, molecular sieves, are best exemplified by zeolites, which are crystalline aluminosilicate compositions, which have very small, well-defined pore and cage structures. In recent years, there have emerged some newer types of molecular sieves, such as the alphos and the sapphos developed by union carbide, and also a variety of pillared compositions. Important catalytic applications for these newer types of molecular sieves are now beginning to surface. The next catalyst type on my list, the membrane reactor catalyst, has not yet received much attention. It consists of compositions that have both membrane and catalyst components. Homogeneous catalysis has long been heralded as an approach that can provide us with some of the exquisite features of enzymes, high activity of mild conditions, and high selectivity. These features were certainly fully realized in the Monsanto acetic acid process and contributed to the exceptionally low unit capital costs of that process. Well, looking broadly at chemical process technology, has homogeneous catalysis fulfilled its promises, has it come of age? I think there's some indication that to some extent it has, and that perhaps the best is yet to come. Several years ago, my former colleague, Dr. Dennis Foster, conducted a review of major new catalytic processes that had been commercialized in the 1970s. It was found that in the manufacture of the top 50 large volume organic chemicals, 17 new processes had emerged in the 70s, and that 11 of these involved a homogeneous catalyst as a key element characterizing the new technology. We see here on this and on the next slide a list of these 17 new processes and an identification of the type of catalysis that was involved in each. Now clearly, homogeneous catalysis has been an approach that has led to a significant number of new processes prior to 1980. Since 1980, the chemical industry has not seen the introduction of many new catalytic processes of any kind, homogeneous or heterogeneous. Now, although they have not been commercialized, several noteworthy new homogeneous catalysts have been discovered. Anionic ruthenium hydrides, new compositions of matter, have been found by Pez and co-workers that reduce nitriles to amines with very high selectivity to primary amines, and they do so at rather mild reaction conditions. Also, this type of catalyst provides the first example of homogeneous catalysis applied to the selective hydrogenolysis of saturated esters to alcohols. This homogeneous reaction also proceeds at reaction conditions that are mild and milder, for example, than the conventional heterogeneous catalysts such as the copper chromides. Industrially, aliphatic amines such as C2 and C3 amines are made by the reaction of the corresponding alcohol and ammonia. Since the alcohols are made from the olefin of the same carbon number, it would seem desirable to avoid the synthesis of the alcohol and make the amine by direct interaction of olefin and ammonia. Just such a reaction by homogeneous catalysis has also been reported by Pez and co-workers for the first time. Soluble inorganic amines promote the direct amination of ethylene or propylene by ammonia to give the corresponding primary amine in both high conversion and high selectivity. The ammonia addition in the case of propylene occurs in a Markovnikov manner so that the product is isopropylamine. It would be potentially useful to have a catalyst that would promote ammonia addition to olefins in an anti-Markovnikov manner. Such a possibility seems to lend itself particularly to homogeneous catalysis, where it is possible to achieve unusual selectivity control via the choice of ligands. Witness, for example, the extraordinary degree of optical stereospecificity that has been achieved in asymmetric hydrogenation catalysis by the choice of ligands. The DuPont company discovered and developed some time ago and has been practicing commercially on a very large scale biohomogeneous catalysis, the anti-Markovnikov addition of HCN to butadiene to produce a diponitride. One can visualize other olefin addition reactions that might be controlled to give preferentially anti-Markovnikov addition in situations where such control has simply not been achieved previously. Recently, Trottle has reported the anti-Markovnikov olefin hydration using soluble platinum complexes. The conversion of synthesis gas to methanol by homogeneous catalysis was reported for the first time a few years ago, and although the selectivity reported and achieved so far is relatively modest, it's a beginning, and it's certainly a worthy target for future catalysis. The present commercial process, as we all know, is a low conversion one limited by thermodynamics. The general area of selective oxidation of hydrocarbons is one that also seems destined to find its breakthroughs via homogeneous catalysis. Dr. James Lyons of Suntech has reported in the last couple of years achieving via homogeneous catalysis a one-step oxidation of propylene to acrylic acid in very high selectivity. This reaction is also applicable to the one-step oxidation of isobutylene to methacrylic acid. Thus, these one-step oxidations contrast with the two-step high-temperature oxidations that are currently practiced commercially using metal oxide catalysts. Zeolites made their first big splash in catalysis as cracking catalysts for petroleum refining. In the past decade, Mobil has developed a variety of ZSM5 that not only convert methanol to high-grade gasoline, but is also being applied commercially with the isomerization of xylenes to paraxylene, the production of ethylbenzene from benzene and ethylene, and the dewaxing of petroleum distillates. Rarely has any single new catalyst or catalyst type had such a breadth of industrial applicability. Furthermore, it's been reported that a modification of ZSM5 can selectively alkylate toluene with ethylene to produce para-ethyltoluene. This in turn can be dehydrogenated to paramethylstyrene, a monomer that should be capable of being produced in large volumes at economics comparable to that of styrene. Polymer made from the paramethylstyrene has been reported to have some property advantages over polystyrene. Thus, a new development in zeolite catalysis may pave the way, or could pave the way, to the development of new large-volume monomer and polymer. A world-scale styrene plant today is of the order of 1 billion pounds per year. Unfortunately, this fact alone provides a major hurdle for any new competitive product to overcome, since scale itself provides a major benefit in the economics of manufacture. Many other new zeolite or non-zeolitic molecular sieve compositions are possible, as well as applications for such materials. Union Carbide has reported the alcohols, which are aluminophosphates, and the sapos, which are crystalline silica aluminophosphates. The latter are ion exchangeable. These new sieves are already yielding new catalytic results. For example, a small-pore aluminophosphate catalyst has been reported to convert methanol to light olefins in high conversion and high selectivity. Selectivities of more than 90% for C2 to C4 olefins has been reported. Catalysts made from medium and large-pore silicone aluminophosphates has given octane improvement in petroleum refining. Most of the applications of zeolites to date have been in hydrocarbon conversion reactions, particularly as applied to petroleum refining. Zeolites should also have utility in the synthesis of chemicals, wherever sites of strong acidity or size selectivity control are desired. To illustrate, Air Products has received a patent teaching the use of zeolites as catalysts for the selective amination of olefins such as ethylene or propylene. It may be possible to achieve the control of aromatic substitution reactions through the use of molecular sieve-based catalysts. The other area of promise cited before was that of membrane reactor catalysis. During the past several decades, most chemical process innovations have been in the reactor end of the process, as expressed, for example, by a new catalytic synthesis technology, while in the separation end, distillation has served as the common workhorse technique. However, I believe that we are at the threshold of some major changes in separation technology, that these changes will have substantial impact broadly on chemical process technology, and that they will include significant shifts from separation by distillation to separation by synthetic membranes and molecular complexes. Although synthetic polymeric membranes have been around for several years, the main industrial application has been in liquid phase separation such as water desalination. Then in 1979, Monsanto successfully introduced commercially gas separation membranes for the recovery of hydrogen. Since then, Monsanto and several other companies have introduced membrane technology for the production and separation of several other gases, including nitrogen, carbon dioxide, and oxygen. There has been a literal explosion of activity in membrane research throughout the world, some of which is strongly aimed at gas separation opportunities. Now, besides their obvious impact in the separation area, I believe that membranes will also become of importance in a fairly new emerging area that I've referred to as membrane reactor catalysis. And the basic premise is that of combining membranes and catalysts. Membranes are capable of achieving separations of incredible subtlety, based in some cases on very small differences in molecular sizes, or in other cases based on marked differences in physical or chemical reactivity. Just as zeolites permit one to combine shape selectivity with catalysis, membranes should allow us to combine any one of several separation pathways with catalysis to achieve new control of reaction selectivity. Based on public disclosures, the most active center of membrane catalysis research is the Soviet Union. A recent 1986 review paper published by Gryaznov reported on the extensive activities that have been underway at many institutions in the Soviet Union at the research, pilot plant, and commercial scale. One of the most heavily targeted areas is that of selective hydrogenation, as applied, for example, to the hydrogenation of acetylic molecules and dienes, the production of vitamin K4, the synthesis of a fragrance known as linalool, and others. It's also been applied to the dehydrogenation of cyclohexane diol to pyrocatechol. Let me quote some euphoric statements from the end of Gryaznov's paper. Thus, membrane catalysts that are permeable only to hydrogen are extremely promising and are unprecedented in actual practice throughout the world. What we have as fundamentally new here is that they are the completed design elements of a commercial reactor. Priority in our country should be given to the use of membrane catalysts in all plants that utilize the selective hydrogenation of acetylic alcohols to ethylenic alcohols, nitro compounds to amines, the hydrogenation of cyclopentadiene to monomer for synthetic rubber. Russian inventors have to date received 58 Soviet invention certificates in this field and 86 patents issued in several Western countries, including the United States. In short, it appears as though the Russians are at the early commercialization stage of membrane catalysis, whereas in the United States we're barely at the exploratory research stage. I'd like to point out a couple of possible opportunities for membrane catalysis not mentioned in the Russian review paper. These are in general in the area of equilibrium-limited reactions, where equilibrium is so unfavorable under ordinary conditions that catalysis is not feasible at reasonable conversion levels. One example is the production of ethylene, the largest volume of organic chemical produced in the world. The one very common method of making ethylene is via the thermal pyrolysis of ethane at very high temperatures of 700 degrees centigrade or higher. This is a fairly brutal process that proceeds in a hot tube and gives rise to a substantial number of undesirable byproducts. The capital intensity of this process is very high and equals or exceeds 50 cents per annual pound of product. In principle, it should be possible to catalytically dehydrogenate ethane at much lower temperatures if the equilibrium constraint could be removed. Can it be developed to give, can a membrane reactor be developed to give such important products of dehydrogenation as ethylene, butadiene, or styrene? There are other industrially important reactions that experience equilibrium control and that might also be attractive candidates for membrane catalysis. These include ammonia synthesis, methanol synthesis, and the water-gas shift reaction. Let me summarize now the vision that I have tried to portray of tomorrow's new developments in catalysis. We will learn how to very selectively oxidize alkanes, for example, methane, methanol, butane, to maleic anhydride or acid, how to directly oxidize olefins with oxygen to epoxides in homogeneous low-temperature systems. We will also learn how to directly promote olefin addition reactions in an anti-Markovnikov manner, how to control aromatic substitution reactions so as to selectively obtain ortho or para derivatives at will, how to catalyze equilibrium-limited reactions at low temperatures, reactions such as dehydrogenation to olefins, methanol synthesis, ammonia synthesis, and others. Most of this will be accomplished by homogeneous catalysis, molecular sieve catalysis, and reactor catalysis. I believe that many of these developments may materialize in the next 10 to 15 years, and that collectively they will comprise advances that will, with advances in separation technology, present us with a new era of novel chemical process technology. At the moment, I'm inclined to believe that many of these new catalytic developments will emerge outside the United States, simply because there is rather limited academic or industrial research underway in the United States directed at the pursuit of many of these opportunities. The reasons for this are certainly rather complex, but I'd like to leave you with two thoughts for consideration for debate. First, these new developments will require discontinuities in catalytic science and technology, rather than incremental type improvements, which are much easier to achieve and comprise the type of advance we are all more comfortable with, that we can afford more readily, given the high cost of research today, both in academia and in industry. Second, newer, more virginal fields of chemical research, such as ceramics, biotechnology, electronic materials, etc., are much earlier in their learning curves, and this tends to project the impression that discoveries in these fields will be easier to make and will be more profitable. But while we are all busily pursuing the tens of billions of dollars of opportunities in these newer areas, who is minding the $1 trillion store for chemical process technology? Thank you.